this is now a part of a chapter called System of Particles. Okay, and the first section of this chapter, which we'll begin with today, is about center of mass. We can refer to as COM or even CM of a system of particles. Now, in order to define center of mass, first of all, let's understand the general concept of what is a system of particles. Okay, how we can classify a system as a system of particles. Any system consisting of multiple particles. Is a system of particles. Example, any rigid body is an example of a system of particles. Whether it's a cube, sphere, a cylinder, rod, whatever be the case. Another example could be like, it need not be a rigid body. Okay? It could be a system of particles. It can also be like a system of individual particles which are somehow connected to each other. So for example, it could be like two particles joined by a light but rigid rod. Okay, so it could be these particles are M1 and M2. They are joined by a rod of length L, but the rod itself is massless. It's very light. So this is another example of a system of particles. In this case, now consisting of just two particles. So that's the general definition of a system of particles. We'll come to definition of center of mass. First, let's understand system of particles, different types of systems, their classification, etc. Okay, now based on this general definition of system of particles, we classify system of particles into two categories. One is called a discrete particle system. So discrete means separate or individual. And the second category is what is called the continuous mass distribution. So as the name suggests, the discrete particle system consists of individual or discrete or separate particles which are located at discrete locations or positions. Okay. So this consists of so an example of a discrete particle system would be something like this. We have three particles that are located at three different points, A, B, and C, of masses m1, m2, and m3. So this is an example of a three particle system, which is therefore a discrete system of particles. Form a triangular shape. On the other hand, a continuous mass distribution is a type of system in which the mass is continuously distributed. That means it's not in separate particles or lumps, but it is distributed continuously in a contiguous kind of manner. So the mass is continuously distributed over the geometrical space occupied by system. So the example is any rigid body, for example, the continuous mass system. It could be in the shape of a cylinder. It could be in the shape of a spherical shell. It could be in the shape of a solid cube. Could be in the shape of a thin rectangular plate. Anything like this. So a rigid body of any shape is an example of a continuous mass distribution. Okay. Now, when we are talking about continuous mass distributions, rigid body is an example, but it need not be a rigid body to qualify as a continuous mass distribution. We could have a non-rigid mass distribution also. For example, we could have a liquid filled in a certain container. So within that container, the liquid is occupying a continuous space, a continuous volume in this case. So that is also a system of particles. This is the classification of system of particles.
Yes, sir.
Okay, so just make a note of this. Hope this is clear. Right, I'll scroll up just a moment. Okay, so we haven't come to center of mass definition yet. Started with understanding the definition of system of particles and then the classification of a system of particles into either what we call a discrete particle system, consisting of discrete or separate or individual particles, versus a continuous mass distribution where the mass is not lumped into individual particles but is continuously distributed over a certain geometry. Yeah, Jitesh, for discrete particle system, your explanation is correct. But when we talk about a continuous mass distribution, rigid body is an example, but a non-rigid body also can be a continuous mass distribution, like
Yes,
fluid.
like any object is taken into
Yes,
play.
basically any continuous distribution where mass is, not in individual particles, but is spread over a certain geometry.
Yes, sir.
It can be spread in the form of a rigid body, it can be spread in the form of a fluid, it can be spread in the form of a gaseous medium, whatever be the case. Okay. But it should be continuously distributed. That's the only idea.
Yes. Yes, sir.
Now, having done these definitions, understood these definitions and classifications, okay. Now let's come to one important property that every system of particles has, and that is it has a special point called the center of mass. Yes, Pratham, you have any doubt, Beta? Okay. Yeah, so every system of particles has a special point called the center of mass. So what is the center of mass? It is a geometrical point within that system, which is the symmetry point. That means the mass distribution is symmetrical with respect to that point. So that is a simple word definition. Of course, we'll understand what we mean by symmetry. Okay. So the center of mass is a geometrical point within the system of particles such that the distribution of mass is symmetrical with respect to it. Okay. So center of mass should not technically be confused with center of gravity, though we will understand in a couple of lectures time that center of gravity coincides with the center of mass as long as the gravitational field we are working with is uniform. Okay. So what is meant by uniform gravitational field and all that we'll discuss in a bit. Okay. But as of now, don't confuse center of mass with center of gravity. Okay. Center of gravity has to do with gravitational force, whereas center of mass is independent of any type of force. It only has to do with distribution of mass for the given system. So it is a symmetry point. Okay. So very good example to understand this symmetry point is that if we have, for example, two identical particles at a fixed distance, okay, that is a system of particles, then where will the center of mass be located? The center of mass will be at the midpoint because that is a symmetry point. So if we take an example, as I just said here, of two identical particles, A and B, of mass m each, and they are located with respect to each other at a fixed distance L, then the center of mass for this system will become the midpoint. Because the masses are equal. Yashovardhan, that's a conditional statement. Whether or not center of gravity and center of mass is at the same point, it depends on something called the gravitational field. Okay, so we'll discuss about that in a bit of time later. But yeah, like generally speaking, for any rigid body on the surface of the Earth, where the gravitational field is uniform, the center of mass is the same as the center of gravity. Center of mass only acts as the center of gravity. But by definition, they are not the same thing, and there's a certain condition in which they are the same. And that condition has to do with gravitational field. Okay, now another example of this kind of symmetry point being the center of mass for a system consisting of identical particles. Another example would be, instead of two particles, now this time, let's say I have four particles which are of identical mass and they are located at the corners of a square. Then very simple, the center of mass,
Diagonals intersect.
yes, it would be what we call the centroid of the square. It would be the point where the diagonals or the perpendicular bisectors. So this time again, we have four identical mass particles. Okay. Just complete this, I'm just coming. Right. So if they are located at the corners of a square, then the center of mass of such a system would be where the diagonals intersect. Or that is also the point where the perpendicular bisectors of the side intersect. And that point is, let's say, O over here, which is the so-called centroid. Okay.
Sir, center of mass will lie at L upon 2, comma L upon 2. Right?
Yeah, if you write it coordinate geometry wise, and in this case, to write it as L by 2, comma L by 2, you will have to take the origin as one of the corners of the square, like the point D. Okay.
Yes.
The center of mass will be at the centroid, which I've labeled as O. The square. Okay. So that is, these are two, you can say super simple examples to understand what we mean by the symmetry point of mass distribution. Because why they are super simple examples? Because we have taken identical particles. Okay. And in the second case, we have taken a very symmetrical shape, which is a square. But now, of course, we'll have to understand what if the shape is not so simple, or what if the particles are not identical? Then what do we mean by this symmetry point? Okay, so we'll discuss about that. Okay, so hope this is clear so far. Okay.
Yes.
Now let us see a situation where we take two particles again, but not necessarily of identical mass. Okay. Suppose this time we have one particle of mass m, and at a certain distance from it we have another particle of mass 3m. These are my particles AB. It's a two particle system, but consisting of different masses which are at a distance L. Okay, so where would the center of mass of this system be?
Like L
It
by
will
3.
be close to 3m.
Closer to
So see, if we are talking about symmetry point for mass distribution, one thing that it makes sense is that the center of mass C will be closer to B, because B is the heavier particle.
yes.
Okay, but then the question is closer by how much?
Uh,
So for example, if instead of m and
the
3m,
center of mass
L by
will
3.
lie in ratio 3:1 on the
very
line.
good. Okay, so for example, if it had been m and 2m, then it would have been again closer to B, but it would have been closer to this geometrical center compared to in this case. No, in this case it
Yes,
is
sir.
further towards. Okay, now
Yes.
another extreme case would be, for example, if the mass of B instead of 3m, it was n times m, and n is tending to infinity, suppose. So the mass of B is infinite compared to the mass of A. Then the center of mass would almost merge with B.
Yes,
Yes.
sir.
Yes, sir.
So how we express this now? So in this case, the center of mass is somewhere here, let's say, such that if this distance is x1 and this distance is x2, then x1 and x2 should be in what ratio? Inverse
Yes,
ratio
sure.
of mass.
3:2.
Yes. Okay. So x1 is to x2 should be, in this case, 3:1, because mass of A is to mass of B is 1:3. So there, okay, so the center of mass divides the distance between them in inverse ratio of mass. Okay, so just complete this. I'm just coming. Okay, so it divides the distance between these two particles in the case of two particle system AB in inverse ratio of their masses. So once we say that x1 is to x2 is 3 is to 1. So we can see here if the total distance between them was L, okay, this distance was L, that means x1 will become 3/4 and x2 will become 1/4. So the center of mass is at a point at a distance 3/4 from A and 1/4 from B.
So A and B are not connected, right?
They can be, they need not be, but if they are connected, it should not be with a heavy rod. It should be with a massless rod. Because it's a heavy rod, then the system center of mass position will change.
Okay, sir.
Right? So, I mean, whether or not they're connected by a light rod, the important thing is that the mass of this system only consists of the mass of these two particles, m and 3m. So the total mass should only be 4m. Okay, so now from this, we will come to the general definition of the center of mass of discrete particle systems. So that is like, I mean, we have seen the definition before, but we will now see a mathematical definition or a formula based on that. So center of mass for discrete particle systems. So let's start by understanding the position of center of mass for a two particle system as a general formula. Now, we've already seen examples above. So from that, we have so we will first write this in scalar form. Then we'll come up with a vector definition of it also. So in the scalar form, if we define the line on which the two particles are lying, okay, as our x-axis, or for that matter, any axis. So we've defined this as our x-axis, and our two particles now are individually located at some positions x1 and m2 at x equal to x2. Then as per our definition, the center of mass should be located at such a point, let's say that is xc, such that it divides the distance between them. If this distance is d1 and this distance is d2, then d1 is to d2 should be equal to m2 is to m1. Or in other words, m1 into d1 from one side should be equal to m2 into d2 from the other side. So now using section formula, if d1 is to d2 is m2 is to m1, then xc will be equal to what? It will be m1 x1 plus m2 x2 divided by m1 plus m2. So this is basically coming from what we call the section formula in coordinate geometry, isn't it?
Yes, sir.
We have two positions and we have a point, so that this distance is in the ratio m is to n. AP is to PB is m is to n. That means the x coordinate of this point P will become m times x2 plus n times x1. divided by m plus n. So this is how we define section formula in coordinate geometry. So that is what we are using over here. So this is an application of section formula. So now in terms of qualitative definition, this section formula gives us the center of mass is the position between the two particles such that its coordinate,
Sir,
yes,
sir, is it necessary that the center of mass will lie in the same plane?
in a two particle system, yes, it is necessary. Okay. In a three particle system also, the particles will either be lying on a line or they'll be lying on a plane, the plane of the triangle formed by them. So the center of mass will have to be coplanar. Okay, understood my point?
Answer, answer.
But the moment we go beyond three particles, they may be non-coplanar. So in that question, in that case, the position of the center of mass does not have to be coplanar with respect to them.
Yes.
Okay. So in a two particle system, okay, the center of mass is such a point, okay, that its coordinate xc is what we call the weighted mean of their individual positions x1 and x2. Where here the weightage is in terms of mass. And that is why for a symmetrical system, the weighted mean position will become the arithmetic mean position. If m1 is equal to m2, then xc will become the arithmetic mean position. So that's another way to understand qualitatively the center of mass of a two particle system. Now we will convert this formula of scalar form, where we have written the position of the two particles in terms of an axis which coincides with their locations. Okay. Now we will convert this into a vector formula where the two particles could be lying anywhere in a general three-dimensional space. Okay. Our x-axis need not be such that the two particles are lying on them. If they have general coordinates x1, y1, z1, and x2, y2, z2 in our rectangular three-dimensional coordinate frame, if the particles are located at any arbitrary points, then how do we locate the center of mass? So we have to just convert this into a vector formula instead of a scalar. So within this section of center of mass of two particle system, we'll now write it in vector form. Okay. We'll complete writing this first. Just back to this. Okay, so let's come to the vector form of the center of mass of a two-particle system. So we will start by visualizing this in a two-dimensional space, but then we will generalize it to 3D later. So suppose in the XY plane, we have two individual particles, okay, which are located at the individual points. So we have M1 just a moment. Yeah, so we have the particle M1, which is located at the position X1, Y1, and we have, let's say, another particle M2, which is located at X2, Y2. So this is the line joining the two particles. So as we know, the center of mass will now be at some point here, let's say, such that its coordinates are, let's say, XC, YC. So the center of mass is dividing this distance between them into D1 and D2 such that M1 D1 is equal to M2 D2. So this distance ratio is the inverse ratio of the masses. So again, by application of section formula, we can see that the coordinates will be M1 X1 plus M2 X2 divided by M1 plus M2, and the Y coordinate will be similarly M1 Y1. So the coordinates are the weighted mean. So when we convert this to a vector formula now, we can see that the vector position of the center of mass, we can express it as a position vector RC. So that will be related to the individual position vectors of the particles M1 and M2. This is position vector R2. This is position vector R1. So now when we write this in vector form, if the position vector of the first particle is R1, the position vector of the second particle is R2, then the position vector of the center of mass will be related to the individual position vectors in such a way that we can write it like this, that the position vector of the center of mass is the weighted mean of the position vectors of the individual particles. You can see that the position vector of the COM, it is the weighted mean of R1 and R2. That is the position vectors of the individual particles. Okay, so just make a note of this, people.
Weighted. Let me explain once again.
Weighted mean means this only, no? Statistically, it is M1 R1 plus M2 R2 divided by M1 plus M2. So weightage is given to the masses. The heavier mass will be closer, the lighter mass will be further away. Whereas if it had been, for example, only R1 plus R2 by 2, that would have been the arithmetic mean position. So it's arithmetic mean only when the masses are equal. So equal weightage is given to.
Yeah, then okay, understood.
Exactly. So these two formulae, Jitesh, are the same thing as this formula. It's just that we've written them in different forms. Here we've written in vector form. Here we've written in terms of coordinate geometry. But
Yes.
they are ultimately the same thing. There's no difference between them. So let's look at an example question. Let's understand the application of this with an example. So particle A of mass 3 kg is located at the point 1, 2 in the xy plane, and another particle B of some mass that we don't know as of now is at, let's say, minus 3 comma y, where its y coordinate is also unknown. So find its mass mb and its y coordinate if the system, that is AB, has its center of mass at the origin O of the xy plane. So very simple question, but an example of class 11th level application of definition of center of mass. Just try this out, people.
Okay.
Certain.
Yes. So tell me the answers.
I
Oh
sent
yeah,
you
I'm
the
getting the
answer.
answers.
So
Yeah, just a
mass
second.
is
So I'll
1
check.
and y coordinate
Y
is
is
minus.
minus 6.
-6.
Yes,
Minus
sir.
6. Yes, very good. That's correct. Okay, so all of you have got this correct. Vedant, Vineet, Jitesh, Soham, Jinendra. So basically, here we have to just use this formula that we want the center of mass to be at the origin. That means xc is equal to 0 and yc is 0. So xc is ma xa, let's say, plus. So in this formula, even though there are two unknowns, the mass of b, oh sorry, there's one unknown. So we'll get the value of mass using this. Okay. So 3 kgs multiplied by 1 plus the unknown mass multiplied by minus 3
Minus.
divided by 3 plus mb should be 0. So this is our first equation, and this will give us that mass of b is equal to 1 kilogram, because the numerator has to become 0 on the right hand side. Okay.
Yes.
And along with that, because y coordinate of the center of mass is 0, that will give us a second equation now from which we'll get the y coordinate of b. So what was A's y coordinate now?
2.
2. Use this. So this formula that we have got in vector form for the three-dimensional for the position of center of mass in terms of weighted mean, this can now be a three-dimensional formula also.
Sir, only we have to add r component now.
Yes, we have to just add the z component. So in three dimension, if R1 is x1 y1 j cap plus z1 k cap, and R2 is similarly having coordinates x2, y2 and z2, then the center of mass will be having coordinates such that and we have to now just add a z component.
The formula will be same, right? RC is equal to.
Yes. So when we convert this vector formula into the individual component formula, we just have to add the z component. Okay, so now let us extend this concept of center of mass for a system of particles consisting of two particles. Now let's extend it to something more general, consisting of any number of particles. Okay, so any general discrete particle system, how we define the center of mass for it. Let's understand that next. So center of mass of a n particle system. So a discrete particle system consisting of a large number of particles, capital N. So if we now try to visualize this system in a three-dimensional space, let's say. So we have our XYZ coordinate system now. The mutually perpendicular rectangular or Cartesian coordinate system. They're all mutually perpendicular. So now if we have scattered in this system or in this space, we have so many different particles, suppose. We have to kind of visualize this in three-dimensional space. So these are not lying on any specific planes like the XY plane or YZ plane or XZ plane. So like this, there are many particles. So the center of mass will be a specific point within that space occupied by all these particles, such that the position of the center of mass such that its position vector is given by the formula m1r1 plus m2r2 plus the summation going up to the last particle of mass mn located at position rn divided by the total mass. Where r1 is the position of particle of mass m1. This becomes the general formula. So as you can see, it is a extension of the formula that we had for two particle system. This also gives us the same information that it is the weighted mean, but it is the weighted mean of a n particle system instead of a two particle system. You can also think of it like this, that position vector of the center of mass is given by a summation formula. Summation of mass into position in the numerator for all particles going from 1 to n divided by another summation in the denominator. Now this summation in the denominator is just the summation of mass. So this is another way of expressing the same formula, such that in scalar form we can write the x coordinate is summation mx divided by summation m. The y coordinate is summation my divided by summation m. And similarly the z coordinate, summation mz divided by total mass. can also express this in coordinate form like this. But it's better to understand it in the position vector form. So this is the vector definition. I is the index of summation, beta. I is called the index number. Okay, so I is taken from 1 to n. That means when we open the summation, the first term will have i's value as 1, then the second term will have i's value as 2, and like that it will go to whatever whole number n or whatever natural number n the series is going up to. So this is the mathematical, expression of summation. Okay, so let's do a quick
Can you
simple problem using this formula.
can you wait for a minute?
Yes.
Yes, you can.
So very simple question next. So we will look at a system consisting of three particles located at the corners of an equilateral triangle, but we won't take the masses to be the same. We'll take the masses to be different. So we have a particle A, which is of mass 2m, another particle B of mass m, and another particle C. Or let's name this particle as D so that we can name the center of mass as m. So ABC is an equilateral triangle of side length L. A is a particle of mass 2m, whereas B and C are particles of mass m each. Locate the position of this system center of mass. Sorry, here I should rename it as ABD. I have taken the third particle's name to be D so that I can keep the center of mass name as C. So had the three masses been equal, then you could have guessed that the center of mass would be what we
Centroid
call
of
the
the triangle.
centroid. So in the case of equilateral triangle, centroid is the same thing as, centroid is the point where the angular bisectors or perpendicular bisectors or altitudes, whichever we choose to call them, because they coincide, those three lines intersect. The altitude is common to the perpendicular bisector, is common to the angular bisectors. So they all these coincide at a common center, which is called the centroid or orthocenter or incenter. All the three types of centers of the triangle coincide in the case of an equilateral triangle. But in this case, the masses are not same. One of them is heavier compared to the other two. So the center of mass will in fact not be at the centroid. So you have to use that summation formula we have discussed above. You have to find it such that it's the weighted mean position of the three particles.
Sir, Sir, done.
So,
Vedant, unfortunately, your answer is not correct. Jitesh, your answer is correct. But Jitesh, you have to tell me where you have taken the origin of your system. Have you taken
Sir.
it at the point D?
D, yes, sir.
Okay. Then the x coordinate is wrong. Just check your x coordinate, beta. The y coordinate is correct, but the x coordinate.
हाँ sir, हाँ sir, हाँ sir. Yes.
Okay. Okay, so now one method of solving this
X
problem
would
would be just use the
X
formula.
would be x upon 2, right?
Yes, L by 2, correct. No. So one would be to make use of the coordinate, the formula that we have seen. So for that, we'll need to define a coordinate frame. So I will define the coordinate frame right now like this. Let's say there are three particles, so they are lying in a two-dimensional plane. So by convenience, we will define our coordinate frame such that they are in the xy plane, and conveniently, this particle D coincides with the origin of my coordinate frame. So if I take my coordinate frame like this, this is my xy plane, then D is the origin of my xy system. So the location of the point B is L comma 0. What about the location of the point A? So for that,
it's
you will
root
see
3L by 2. I understand.
yes,
L by
now
2.
use the geometry that this is 60 degrees. Okay, so the x coordinate of A will become
Root 3L by 2.
yes, L cos 60, and the y coordinate of A will of course be L. So this will be at root 3 by 2 L comma L. Okay,
Yes, sir.
okay, so now the center of mass will be at a position such that the x coordinate of the center of mass is summation mx divided by summation m. So when we write that over here, we should write it as maxa plus mb into x of b plus mass of d into x of d divided by the total mass. Okay, so when we incorporate that here, A's contribution is m into 0, B's contribution is m into L, C's contribution is okay. So now see, this is where we have got this is wrong. A's x coordinate is not L cos 60 beta.
That's the
Sir,
y.
A's x coordinate is L by
That's L by 2.
his y coordinate is root 3 by 2L. This is L sine 60, in fact.
Yes, sir. Now it makes sense.
Now is correct. Yes. Okay. So this one will be the when we write it in proper order, E's contribution is 2m into L by 2. B's contribution is m into L. D's contribution is m into 0 divided by the total mass. So how much that is becoming? That's L by 2.
Yes.
Similarly, y coordinate. Let's write that directly. So A's is 2m into root 3 by 2L. B's and D's are both 0. But divided by the total mass, which is 4m. So this becomes how much now? Becomes root 3 by 4. So the center of mass is located at the position L by 2, comma root 3 by 4L. So that means my center of mass is somewhere here, such that this coordinate is L by 2. And this coordinate is exactly half of this.
Yes, sir.
This. So this is one way of solving the problem. Now, in this we have basically made use of the formula and kind of use brute force kind of method. But there was a certain symmetry, and that symmetry was that B and D are of identical mass and A is double that mass. So we can also make use of that symmetry and simplify the solution. So typically what happens is in this chapter, we have to always look for symmetry in a given problem and try to make use of that symmetry so that we don't have to use such a lengthy formula based method. Okay, so now let's also see alternately how we could have made use of the symmetry of the problem, come up with something simpler. So now instead of first finding the center of mass of the whole system ABC, if we had done this, that we first notice that this is B and D are a two particle system which are identical. So their center of mass will be where? At the midpoint?
Yes.
Yes, sir.
So now we can use that and say that this system is equivalent to,
Sir,
yes,
sir, the center of mass could be the centroid also.
no, it is not the centroid, brother, because the
Mass
masses are not
अलग है
equal.
ना.
A, B and D. You understanding the point?
Yeah, sir.
A का मास अगर M होता ना तो फिर centroid होता.
Okay, sir.
I can replace B and D with a 2m particle located here. So this is B plus D. And I can leave A the way it is, which is a 2m particle here. So now where is the system center of mass? The system center of mass is at the midpoint of this.
Yes, sir.
हाँ, sir.
So this distance should be equal to this distance, which is half of the altitude. So now coming back here in the original triangle, I can see that the center of mass will be on the vertical altitude or on the bisector of the perpendicular bisector of BD, but at a height of this thing. This will be the center of mass. So this is another way of solving the question. Okay.
Yes, sir.
Just make a note of this. So this is using the symmetry of the problem. What is the symmetry? That mass of B is equal to mass of D, that is M. Okay. And the fact that mass of A is 2M. So it is equal to the mass of B plus the mass of D. It is now, that is the question of like motion of the center of mass. We'll come to that. So in a specific situation, the center of mass can move in any way required.
Yes, sir.
Now, one more thing we should understand here, that if mass of A had been equal to M, that is mass of A is equal to mass of B is equal to mass of D in the above problem, then the center of mass C would be at the centroid of triangle ABD. So it would have been at L by 2 comma L by root 3. Sorry, L by 2 root 3. But that would have been in the case where all three masses are equal.
Yes, sir. Done that.
You understood this now?
Sir.
Okay, now next example, let's understand something which will give us an idea about how the center of mass moves in case the individual particles of the system are moving. So in our next example, our system is very simple one consisting of two particles on the x-axis. So let's say we have two individual particles A and B, which are of identical mass, located at x A equal to 3 and x B equal to 5. X is in meters. So A and B are of identical mass m each. So this is how they are located at t equal to 0, time t equal to 0. Now at a new time, let's say t equal to t, B has moved here. It has moved to the position B prime, where its position has become 6, whereas A has remained stationary. So find the displacement of the center of mass.
Sure.
Yes.
Can I answer?
You sent the answer?
Then
Yes, that's correct. Okay. So one simple way of doing this problem is find the position of the center of mass at t equal to 0, and then find it again at the new time t equal to t. And from that you can find the displacement of the center of mass. Yes, that's correct. Vedant and Soham. The answer we will get is that the displacement of the center of mass,
0.5.
yes, is 0.5 meters along the positive x-axis. Or if we want to write it in vector form, like this. So one way of solving this is that you just locate the position of the center of mass initially and then find it again at t equal to t.
Sir, we can find by differentiating also, no?
By applying the concept of change.
Ha.
so like
Differentiating
relative
will give you rate of change. Okay, so that would give you velocity, but we don't have information about velocity here. If we assume that, for example, B has moved with uniform velocity, then we can find during that time what is the uniform velocity of this one also.
So you said the COM divides the 2 points by the ratio inverse to the mass.
Yes.
Since the mass is equal, so the COM will be at the midpoint.
Yes. Okay.
That was
So
the reason.
initially at t equal to 0, where is the center of mass located? It is located at 4. Okay. But now when we come to the new time, A is located at here only. A has not moved. A's position has remained 3, but B's position has changed to 6. So now where the center of mass has gone?
4.5.
Yes. The center of mass in this case now has moved to this position, which is 4.5 meters. So you can understand that in comparison to B, the center of mass's displacement is half. This is the displacement of center of mass. Whereas this is the displacement of B. So you can also understand this in this way, that this is the general formula. So displacement of the center of mass will be change in the position of the center of mass. So that will be delta of this whole quantity. So when we calculate, when we take the delta inside the bracket here, it becomes MA into delta XA plus MB into delta XB divided by MA plus MB. This is the general formula. Okay. So displacement of the center of mass becomes mass into displacement of A plus mass into displacement of B divided by summation of the masses. So this step to this step we have done because in general, MA and MB are constants, are fixed masses, but XA and XB can be changing. So this is like a general formula.
Sir,
Okay, so here, yeah.
just like extra thing, if both the particles are moving with different constant velocities, then we can take it by relative velocities, like relative motion. I think.
Not by relative velocity, because better see what we are doing is now we are locating the velocity of the center of mass with respect to
M1,
ground,
V1.
not with respect to one of them. You're understanding my point?
Sir.
In which case we'll use relative velocity. If we want to find the relative velocity of the center of mass with respect to A, and A and B are moving,
Okay.
then what we'll do, we'll find the relative velocity of B and use the formula for velocity of center of mass. Okay. But
Yes,
if we
sir.
want to find the velocity of the center of mass in the ground frame, then we don't look at the relative velocities. We look at the individual velocities of A and B in the ground frame only.
Okay.
So the general vector formula here, we can write like this. Position vector of center of mass for a two-particle system So displacement is defined as change in position. So once again, it is delta of that weighted mean M1 R1 plus M2 R2 divided by M1 plus M2. So when we operate this delta onto this bracket by opening it, you can see that again M1 and M2 will be treated like constants. So it will become M1 into delta R1 plus M2 into delta R2 divided by M1 plus M2. And delta R1 and delta R2 are nothing but the individual displacements of particle 1 and 2 with respect to the ground frame. So again, it becomes like a weighted mean, just like we've written in the scalar form above, that the displacement is MASA plus MBSB. So like that, it now becomes a vector relation. Okay, so we are going from this step to this step because M1 and M2 are constant masses, constant or fixed masses. This is the displacement formula of center of mass taken a two particle system. So of course, if we generalize it to an n particle system, then again we just replace the numerator with summation of mass into displacement and replace the denominator with total mass or summation of masses, m1, m2, m3, up to whatever number of particles. Okay. Similarly, for example, if we want to find the velocity of the center of mass, then instead of applying delta to position, we'll apply d by dt or rate of change. So we will see that it becomes the weighted mean of the velocities. Like the displacement is the weighted mean of the individual displacements. Okay, and so on and so forth. So we'll discuss more about this in the next lecture coming up. We have another lecture this week.
Yes, sir.
Okay, so
So
in the
I'll
meantime,
apply d by dt to SC, right? For velocity.
SC or RC is one and the same thing. Okay, remember that instantaneous rate of change of position is the same thing as instantaneous rate of change of displacement. You know?
Sir, if we will
Yes, sir.
differentiate with respect to v, then we will get acceleration also.
Then we'll get acceleration. So again, differentiate this relation that we've written right now. So you get instantaneous velocity, and then differentiate that relation with respect to time, and you get instantaneous acceleration.
Sir.
Okay, yeah. So in the meantime, before next lecture, please complete any pending questions in circular motion so that if required, you can discuss the doubts. And I will send you a list of specific things. You can start reading center of mass theory from Resnick-Halliday or NCERT, whichever you find convenient. Resnick-Halliday is better. And you can start doing some of the questions based on calculation of center of mass position from H.C. Verma's exercise. In H.C. Verma, this chapter is called System of Particles. It comes after work by energy.
Yes, sir.
You can start with that also. So that's it for today's session. Wish you all the best and have a nice day.
Thank you, sir.
Bye.
Thank you, sir.